All right, here I am again, talking to the open living room about calculus. This goes with our recap number 4. So these are your multiple choice questions from AP Classroom. The graph of the derivative of f is shown in the figure above. So we're looking at an f prime. Which of the following could be the graph of f? So when I look at this, f prime is positive between -2 and 2, which means my function needs to increase from -2 to 2. My function is decreasing from -infinity until -2 and from 2 until infinity. I have a minimum at x equals -2, and I have a maximum at x equals 2, and looks like I have a point of inflection at x equals 0. Well, this one is not interesting enough, right? This one is strictly increasing, doesn't even have a change. This one's strictly decreasing, doesn't even have a change. This one, I'm supposed to have minimum there and maximum there, so that can't be it. This one, I'm supposed to have minimum there and maximum there, so that can't be it. So it looks like we have answer choice E, decreasing, where we're supposed to be decreasing, increasing, where we're supposed to be increasing, minimum, maximum, point of inflection. That was supposed to be yellow, point of inflection. All right, next one. Let f of x equal this integral. Well, remember, if f equals the antiderivative of this, right, then this thing is equal to the derivative of this. What value of f of x is f of x a minimum? So we're looking for an x value where f is at its lowest. Well, if we are looking for a minimum in calculus, we need to know where f prime changes negative to positive or at endpoints. But we don't have any endpoints here for absolutes, so we are just going to do a first derivative test. Okay, well, that got messed up because I had to pause and go back. Value of x is equal to question mark. F being a minimum means f prime changes negative to positive or endpoints, which you just heard me say. So great. We need to do a first derivative test on this guy. So the derivative of f of x is f prime of x, for how we notate that. The derivative of an integral, remember we can use the shortcut. So into e, I just replace my t with that top function, and then I have to multiply by the derivative of that function. And then this had been a constant, so that would have canceled out, and we're all good to go. So I want to know where this changes from negative to positive, so I need to find my critical numbers. E to anything is never going to be equal to 0, so I just really need to figure out where 2x minus 3 is equal to 0, which happens to be at 3/2. If I wanted to be very careful, I could check, plot my f prime number line, plot 3/2, pick a number to the left and to the right. This whole thing is always going to be something positive because our exponent is positive, and then we're going to have e to a positive. So if I pick, let's say 0, 0 minus 3 is a negative. If I pick 5, 10 minus 3 is a positive. We do in fact have a minimum when x is equal to 3/2. So that's one of those fundamental theorem of calculus shortcuts that you've got to be able to do, where you just plug in the upper bound into that variable times the derivative of the upper bound, because the chain rule that would have been in play. For all x in the closed interval from 2 to 5, the function has a positive first derivative, which means our values are increasing, and a negative second derivative. So they are increasing at a decreasing rate. Weird. Which of the following could be a table for f? So they need to be getting bigger, but at smaller rates. So in this one, they are getting bigger. So that's a contender. This is a +2, this is a +3, this is a +4. The rate of change is actually increasing, so that we got to throw out. This is a +4, a +3, a +2. This is potential, and hint, it's in green with a check mark. We've got that. These values are going down, garbage. These values are going down, garbage. These values are going down, garbage. So B, it is. We are increasing. Our values are going up, but the rate is going down. All right, table above gives us values of a function and its derivative. If f prime is continuous on the interval, remember if f prime is continuous, that means that f was differentiable. F was f was differentiable. What is the value of this guy? Well, I want to take the antiderivative of f prime. So using the first fundamental theorem, that's going to result in the layer above evaluated at b minus the layer above evaluated at a. F of b minus f of a. So f of -1 is -1.5 minus f of -4 is 0.75. -1.5 minus 3/4 is equal to -2.25. So again, this is the first fundamental theorem. The antiderivative of f prime is equal to f evaluated from a to b. Last one, the graph of f is shown and has horizontal tangents at 3 and at 6. If g is equal to this, what is the value of g prime of 3? Well, if g is the antiderivative, then f is the derivative of g. So this is looking at some sort of a g prime graph. But officially, to take the derivative, because I want g prime of 3, which means I could start by finding g prime of x. I'm going to use that shortcut again. G prime is going to equal f of 2x times 2. So I take that top bound, I'm going to sub it in for my variable, and then times the derivative of 2x. So I wanted g prime of 3, so that's going to be equal to f of 6 times 2. F of 6, 1, 2, 3, 4, 5, 6. F of 6 is equal to -1. -1 times 2 is -2. So again, that shortcut, when you take the derivative with respect to x, this will be some number, and let's say this is some function. The shortcut is you just take this function, sub it in for t, times the derivative of that function. It's the chain rule that's coming into play. All right, that's it. Hopefully that helps. Let your teacher know if you have any questions.